Now I use a trick. So my idea tree is a trick. And the trick says that I know something very interesting and using that something very interesting, could I get something out of it? So let's write down the same equations that we saw the last time. So this is what we called as the Bellman equation. It specifies a constraint between an entity and all its possible successors. And the Bellman equation, of course, has something which is hidden inside it, which is a constraint that every state S is interlinked, it's connected to the state S dash, and we used exactly the same trick that we used the last time to make in the value iteration algorithm, the policy iteration algorithm, and everything up. So let's use the same trick. What's the problem is that it has probabilities. Okay, last time I denoted it by P. I said that P and T, I use them interchangeably because last time it was P using a P. So the problem is that I need to get rid of this probability. So let me model it a bit differently. So basic learning equation, everybody knows that. So what do? I make an observation from state S. I apply an action A and nature selects a state that I land into, that's S dash. I didn't select it, nature did. So I can observe the rewards. Now, rewards are an input to reinforcement learning. That's the only input. You cannot get rid of it. So I know the rewards. You have to model the problem to know the rewards. And now I'm thinking that, okay, from this observation, can I learn something? Is there something hidden in this observation? Yes, that's the Bellman equation. So from S to S dash, there are some linkages, and that's what I'll try to learn. So I say that utility of S, the new value, so time t plus 1 is equal to utility of S, the old value, plus learning rate times, that's your learning rate, covered in the other course, so I can directly write down, times the error. So that's the thing that I'll use for learning. I'll get a new estimate based on the new old estimate plus the error that I see. So I look at some error and I make in some corrections because of that in my model. So let's define the error. So utility of T plus S is utility of S plus learning rate times. So I say, what is the utility that I observed? What's my new observed utility minus what was my old estimate of utility? That's how I define the error. What did I observe minus what's the old value? And let's solve this up further. So what's my observed? All that I know is from state S, I got a reward of RSA S dash. I reached a state S dash, and S dash to goal or S dash to terminal is a utility of S dash. And I'll discount it up, so I'll say gamma times this. So this becomes equal to utility of S plus alpha times observed is this plus this, or SAS dash plus gamma times utility of S dash minus what's the old estimate, utility of TS. And this one is what is called as the temporal difference learning, or the TD learning. And it's exactly same as the supervised learning that you have seen so far. So I need not tell you what are the different parameters and how do they behave. But one thing that should be pretty inquisitive to you for an obvious reason is, let's compare the two equations. So ideally what happens is that my error value becomes 0, or this should be the target value of my UT. So let's compare UT is U convergent S with this value. So you see RSAS dash, you see RSAS dash, you see gamma, you see gamma, you see U of S dash, you see U of S dash. However, where did the probability go? There's no probability over here. And if you just look at it, it gives you an impression that the probability has suddenly become equal to 1. So it suddenly a probability becomes equal to 1. The other thing is that where did max A go? So let's answer both of them one by one. So the problem with this is, 1, actions are gone, 2, probabilities are gone. So let's say where did action A go? Now I'll be talking about actions a lot of time. For now, let me just cheat and fix it. So let me do a cheating and let me fix in the actions. And that's cheating. I'll get rid of my cheating later. So I say that my learning is more specifically called as passive reinforcement learning, where the term passive means that the actions will be given, or it means that an intelligent technique, which for now could only be a human, selects best as per its own judgment actions. So action selection is done by someone intelligent, and the reinforcement learning only learns utilities for the given actions. So talking more in easier language, what is passive reinforcement learning? Passive reinforcement learning is when someone is taking the action. So somebody is driving the car for learning how to drive. That's not you. Somebody is playing the game. That's not you. Somebody is giving question answer interview session. That's not you. Somebody is walking. That's not you. So somebody is doing all the best things, And you as a child are just looking at what is going on and learning the utilities in your head by a mere observation of what this person is doing. Luckily, I started off with games, so let all the volunteers play games, which is your batchmates. Your machine learning technique, passive reinforcement learning, will just sit and observe what's going on, and through that, it will know what the utility is. The assumption is that all these are the best players of the game, otherwise, they take bad action and you learn anything up. Later on, what I will do is, of course, I'll change it into active reinforcement learning, where what will happen is that the reinforcement learning technique move the agent, or select the actions and learn the utilities, policies. So both of them happen simultaneously. I only play the game, I only learn it. The video game is under my hands. I am playing it and I'm learning from what I do. I am working and I'm learning what to do. I am giving this question paper interview thing and I am learning what to do. So actions are from me and observations is mine, and I learn the utilities and the policy. So as of now, we know whether this max A goes. It's passive reinforcement learning. And because it's passive reinforcement learning, I say that, okay, somebody selects that for me. We'll soon change that. Now the interesting thing is, where did the probability go? Otherwise, it just appears that the probabilities have become a 1, which is completely bad. So I want to find out where did the probabilities go in this equation. Let us take a dummy example and say this was my state S, and I fixed the action to be up, and this becomes my either of these three states S dash. And to give it numbers, let us say this is 2 1, this is 3 1, and this is 1 1, and this is 2 2, and my action is fixed to be up. And in order to learn this equation, we are learning u of s. So let s be fixed to 2 1. Action selected by the intelligent technique is always up. And using that, let's see how will these equation end up behaving. So now thing is that I don't select S dash. God selects it up. However, because I know probability of S dash is equal to 2 2 given 2 1 up is equal to 0.8. Algorithm doesn't know that, God knows it. And similarly, 1 1 is 0.1. I don't know it, God knows it. And 3 1 is 0.1. I don't know it, God knows it. So out of everything that I observe, I streamline to only s is equal to 2 1 and a is equal to up. And let's write down these equations again. So ut plus 1s is equal to uts plus alpha t times r. S action is up, a dash 2 plus gamma times utility of 2 minus utility T of S, and this equation will be applied 80% of the times, because 80% times God will select 2, and similarly utility of S will be utility of S plus alpha T times S A S dash 1 plus gamma times utility of 1 minus utility of T of S. I'm not writing S is equal to 2 because it's obvious, and similarly for the L. So this one will happen 10 times, and alpha T times S A S dash 1 plus gamma times utility of 1 minus utility of T of S. This will happen 10% times. Now we know because time is iterative, so let's say 3 consecutive actions were this, this and this. So basically what happens is the old value here is the updated value here. The old value here is the updated value here, and you solve this equations. Imagine this correction happens 80% of the time, this correction happens 10% of the time, this correction happens 10% of the time. The total correction is like doing all the corrections and averaging it out. That's what you do in supervised learning. That's what you learned in supervised learning. There was a lot of data. There was huge amount of data. So you applied correction for each and every data, each and every batch, and the result was more or less like taking the average corrections of all of them and updating your weights. So same thing around over here. It's like doing 80% of the corrections because of this equation where you have the 2, doing 10% because of this where you have 1, and doing 10% because of this where you have 3, 1. All 80% of the time my data is learned from non-slipping case 2, so its effect is more profound. 10% it's selected based on the other 2, which is these 2, and its effect is less profound. 10% due to left slip, 10% due to right slip, and the effective measure because of the same kind of averaging will be 80% times 2, 10% times 1, 10% times 3, 1, which is same as multiplying the probabilities around over here, weighted average, weighted by probabilities. So it seems to be doing the correct thing. Again, the wonderful thing. So I didn't supply the probability. Who did? There's no probability over here. It's getting effective. Who did? God did. God is selecting S dash by the natural probability. 80% without slip, 10% left slip, 10% right slip. So imagine a huge database of supervised learning, which by now you are used to. So 80% of the data God has selected, sampled by God's algorithm, which corresponds to the no slippage, so that adds the maximum efforts. 10% by the other 2, and because God is sampling the data, the probability measures by the natural God-defined probability are getting into it most naturally, and therefore you really don't need to define the probability over here. God takes care of it. And because God takes care of it, that's all right. The only thing, of course, you don't want is a very high learning rate, in which case the newer data is a lot more important. And what you do need is slowly decaying learning rate so as to imitate the natural God selected probabilities.